From the earliest attempts to understand matter, electric charge appeared as one of the most obvious and powerful properties in nature. Long before atoms were known to exist, humans observed attraction and repulsion through rubbed amber, lightning in the sky, and sparks jumping between metals. When science finally uncovered the atomic world, it became clear that charge was not just a surface phenomenon, but a deep organizing principle of reality. Inside every atom, charged particles govern structure, interaction, and behavior. Yet, hidden among them is a particle that seems to defy this pattern: the neutron. Understanding the mystery of electric charge and why neutrons are different opens a doorway into the true architecture of matter. Electric charge is a fundamental property, meaning it cannot be reduced to anything simpler. Particles either possess positive charge, negative charge, or none at all. Protons carry a positive charge, electrons carry a negative charge, and these two particles dominate most of what we experience as matter. Their attraction binds electrons to nuclei, forming atoms. Their repulsion shapes the size of atoms, the behavior of electricity, and the chemistry of life. Because charge is so influential, early atomic models assumed that every fundamental particle must carry some form of charge. The discovery of the neutron challenged this assumption in a profound way. Before neutrons were discovered, scientists believed atoms consisted only of protons and electrons. However, this model had serious problems. Atomic masses did not match the number of protons alone, and nuclei with many protons should have been violently unstable due to strong electric repulsion. Something was missing. In 1932, James Chadwick's discovery of the neutron solved these puzzles at once. Here was a particle with nearly the same mass as a proton but no electric charge. It added mass without adding repulsion. This single fact revolutionized nuclear physics and reshaped our understanding of atomic structure. The mystery deepens when we ask why electric charge exists at all. Charge determines how particles interact through the electromagnetic force, one of the four fundamental forces of nature. This force is long-range and powerful, far stronger than gravity at the atomic scale. Because of this, charged particles strongly influence each other even across relatively large distances. Neutral particles, by contrast, are invisible to electromagnetic attraction and repulsion. The neutron's lack of charge means it does not participate in this force in the usual way. This raises an important question. Why would nature include a particle that is massive, central to the atom, yet electrically silent? The answer lies in balance. If all particles in the nucleus carried charge, the nucleus could not exist in a stable form. Protons repel each other with increasing force as more are added to the nucleus. Without a neutral partner, atoms heavier than hydrogen would be impossible. The neutron exists precisely to solve this problem. Its neutrality allows it to sit between protons, contributing to nuclear cohesion without increasing electrical conflict. In this sense, the neutron is not an exception to the rule of charge, but a necessary counterpart to it. To truly understand why neutrons are neutral, we must look beneath the surface of particles themselves. Modern physics reveals that protons and neutrons are made of quarks, smaller constituents bound together by the strong nuclear force. A proton contains 2 up quarks and 1 down quark, giving it a total positive charge. A neutron, by contrast, contains 1 up quark and 2 down quarks. The charges of these quarks cancel exactly, resulting in 0 net charge. This precise cancellation is not random. It reflects deep symmetries in the laws of physics, suggesting that charge neutrality at the neutron level is a built-in feature of nature's design. Despite having no charge, neutrons are not passive. Their presence dramatically alters the behavior of nuclei. In fact, the stability of nearly every element depends on the correct balance between charged and uncharged particles. Too few neutrons, and the repulsion between protons overwhelms the nucleus. Too many neutrons, and the nucleus becomes unstable in another way, leading to radioactive decay. The neutron's difference from charged particles allows it to act as a stabilizer, a regulator, and sometimes a trigger for transformation. The contrast between charged and neutral particles also reveals something profound about forces in nature. Charged particles interact through electromagnetism, which can act over long distances. Neutrons lacking charge are unaffected by electric fields and magnetic forces in the same way. This allows them to approach nuclei closely without being repelled. It is one reason neutrons are so effective in initiating nuclear reactions. Their neutrality lets them cross barriers that charged particles cannot. This property would be impossible if neutrons carried even a small electric charge. On a deeper level, the neutron challenges our intuitive understanding of identity. We often associate influence with visibility, power with force, and interaction with charge. The neutron shows that absence can be just as important as presence. Its lack of charge is not a weakness, but a defining strength. It allows the neutron to operate in regions where charged particles would fail. This principle appears repeatedly in physics, where symmetry, cancellation, and neutrality enable stability and complexity. The existence of neutrons also explains why electric charge appears quantized and balanced in nature. Atoms are electrically neutral overall because the positive charges of protons are exactly balanced by the negative charges of electrons. Within the nucleus, neutrons ensure that this balance can exist without structural collapse. They separate the concept of mass from the concept of charge, showing that these properties, while often linked, are fundamentally independent. As atomic numbers increase, the importance of neutrons grows. Light atoms can survive with nearly equal numbers of protons and neutrons, but heavier atoms require more neutrons to remain stable. This reveals that neutrality becomes more crucial as systems grow more complex. The neutron's difference from charged particles becomes more pronounced, not less, as atomic structure becomes richer. Without neutrons, the periodic table would end almost before it began. In the broader picture of the universe, the mystery of electric charge and neutron neutrality shapes everything from the formation of stars to the existence of life. In stellar cores, neutrons help build heavier elements. In extreme cosmic environments, matter can become so dense that neutrons dominate entirely, forming neutron stars. These objects demonstrate what happens when neutrality overwhelms charge, producing states of matter unlike anything else in the universe. Ultimately, the neutron's lack of charge is not an odd exception, but a fundamental necessity. It reveals that nature values balance over uniformity, stability over simplicity. By being different, by carrying no charge in a world ruled by charge, the neutron makes the atomic universe possible. Its neutrality is the quiet answer to one of physics' oldest questions: how can matter hold itself together at all? When we look more closely at the mystery of electric charge, we begin to realize that charge is not merely a label attached to particles, but a deep rule that governs how matter organizes itself. Charged particles announce their presence loudly. They push, pull, repel, and attract in ways that are easy to detect. From the spark of static electricity to the glow of a light bulb, charge makes itself known. In contrast, the neutron exists in quiet contrast, carrying mass, momentum, and influence, yet remaining electrically invisible. This contrast is not accidental. It reveals a layered structure in nature where different properties play different roles. In the early development of atomic theory, scientists struggled to reconcile measured atomic masses with observed charges. Elements were identified by their chemical behavior, which depended on electrons and protons, yet their masses were far larger than expected if only those charged particles were present. The idea that a neutral particle could exist inside the nucleus initially seemed strange because neutrality felt like nothingness. However, experiments soon showed that neutrality could coexist with substance. Neutrons scatter particles, transfer energy, and contribute gravity, all without electric interaction. This realization forced physics to separate the idea of influence from the idea of charge. The more scientists studied electric charge, the clearer it became that it operates under strict conservation laws. Charge is never created or destroyed, it is only transferred. This conservation gives the universe stability and predictability. Neutrons fit perfectly into this picture. By carrying no net charge, they neither violate nor complicate charge conservation. Instead, they allow charge to be distributed in a way that supports complex structures. Without neutrons, charge conservation alone would not be enough to keep nuclei intact. One of the most fascinating aspects of the neutron's difference lies in how it interacts with space itself. Electric charge creates electric fields that extend outward indefinitely. A proton's influence can be felt far beyond the nucleus, shaping electron orbits and chemical bonds. A neutron creates no such field. Its presence is localized, intimate, confined to the nuclear interior. This difference allows nature to separate long-range order from short-range stability. Charged particles govern the large-scale structure of atoms and molecules, while neutrons govern the deep internal stability of nuclei. This division of roles shows that neutrality is not a lack but a specialization. The neutron is designed, by the laws of physics, to work where charge would be destructive. Inside the nucleus, distances are unimaginably small. At that scale, electromagnetic repulsion between protons becomes enormous. Introducing another charged particle would only worsen the problem. The neutron, by being neutral, avoids adding to this repulsion while still participating in the strong nuclear force. This makes it uniquely suited to the nuclear environment. The difference between neutrons and charged particles also becomes clear in experiments involving radiation. Alpha particles, which are positively charged, are easily deflected by electric fields. Beta particles, which are electrons or positrons, curve dramatically in magnetic fields. Neutrons, however, pass straight through such fields, unaffected. This behavior once puzzled researchers, but later became a powerful tool. Because neutrons ignore electric barriers, they can probe materials, penetrate nuclei, and initiate reactions that charged particles cannot. Their neutrality opens doors that charge keeps closed. On a philosophical level, the neutron challenges the human tendency to equate importance with visibility. Electric charge is dramatic and easy to demonstrate, while neutrality appears boring at first glance. Yet the neutron shows that the most critical roles in nature are often hidden. By not interacting electromagnetically, neutrons avoid interference. They act silently, efficiently, and decisively. This hidden influence mirrors many natural systems where balance is maintained not by forceful action, but by quiet regulation. As nuclei grow larger, the difference between charged and neutral particles becomes even more critical. Heavy elements require significantly more neutrons than protons to remain stable. This is because as the number of protons increases, their mutual repulsion grows rapidly. Neutrons counteract this trend by increasing the binding through the strong force without increasing electrical stress. The neutron's neutrality becomes more valuable, not less, as complexity increases. In this way, the neutron enables the existence of the rich diversity of elements found in nature. The mystery of charge also extends into the early universe. In the moments after the Big Bang, matter existed in an extremely hot, dense state. Protons and neutrons formed in nearly equal numbers. As the universe cooled, their balance determined which elements could form. If neutrons had carried charge, even a small amount, this delicate process would have been radically different. The elemental composition of the universe, including the carbon and oxygen essential for life, depends on the neutron being exactly neutral. Modern physics continues to test whether the neutron is perfectly neutral or only neutral to an extraordinary degree. Experiments have placed incredibly strict limits on any possible charge the neutron might have. So far, all results are consistent with complete neutrality. This precision suggests that neutrality is not an approximation but a fundamental rule. Nature seems to demand that the neutron be electrically silent to an astonishing degree of accuracy. In understanding why neutrons are different, we also gain insight into the layered nature of physical laws. Electromagnetism dominates at the scale of atoms and molecules, shaping chemistry and biology. The strong nuclear force dominates at the scale of nuclei, shaping elements and energy. Neutrons sit at the boundary between these worlds. Their lack of charge frees them from electromagnetic dominance, while allowing them to fully engage with the strong force. They are the bridge between forces, the mediator between mass and stability. Ultimately, the mystery of electric charge and the neutron's difference teaches us that nature values harmony over uniformity. Not every particle must carry the same properties. Diversity at the fundamental level enables complexity at every higher level. The neutron's neutrality allows atoms to exist, elements to form, stars to shine, and life to emerge. In a universe ruled by charge, the uncharged neutron proves that sometimes the most powerful role is played by the particle that does not push or pull, but simply holds everything together. When we move from the visible behavior of particles to their internal structure, the neutron becomes even more fascinating. At first glance, calling a particle neutral sounds simple, almost empty, as if nothing is happening inside it. But modern physics shows that the neutron is anything but empty. Its neutrality hides a complex internal world, governed by precise rules and powerful forces. Understanding what is inside the neutron and how its structure leads to zero electric charge reveals how deeply ordered the universe truly is. For a long time, scientists believed that protons, neutrons, and electrons were fundamental, indivisible building blocks of matter. This view began to change in the mid-20th century, when experiments revealed that protons and neutrons themselves had internal structure. High-energy particle collisions showed that these particles could be broken apart, not into smaller pieces in the everyday sense, but into more fundamental constituents called quarks. This discovery completely transformed nuclear physics and provided the key to understanding why neutrons carry no charge. Quarks are extraordinary entities. They are never found alone in nature, only bound together in groups. Each quark carries a fractional electric charge, something that once seemed impossible because all known charges appeared in whole units. There are different types of quarks, but the neutron is built from just two kinds: up quarks and down quarks. An up quark carries a positive charge of 2/3, while a down quark carries a negative charge of 1/3. These values may seem strange, but they are essential to the internal balance of matter. Inside a neutron, one up quark and two down quarks are bound together. When their charges are added, the result is exactly zero. The positive 2/3 charge of the up quark is cancelled by the combined negative 2/3 charge of the two down quarks. This cancellation is exact, not approximate. It is not the result of chance, but of deep symmetries in the laws of physics. The neutron's neutrality emerges naturally from its internal composition, showing that neutrality can arise from complexity rather than simplicity. What holds these quarks together is the strong nuclear force, one of the most powerful forces in nature. At the quark level, this force is described by a theory known as quantum chromodynamics. In this theory, quarks interact by exchanging particles called gluons. Gluons act like invisible threads, binding quarks so tightly that they cannot escape. This binding is so strong that attempting to pull quarks apart only creates new quark-antiquark pairs, rather than isolating a single quark. Inside the neutron, this force is constantly at work, maintaining the precise arrangement that results in zero net charge. Despite being neutral overall, the neutron is not electrically uniform inside. The quarks within it are charged, and their motion creates subtle internal distributions of positive and negative charge. This means the neutron has a complex internal electromagnetic structure, even though its total charge is zero. Experiments have shown that different regions inside the neutron can momentarily exhibit slight charge imbalances. These effects are tiny and short-lived, but they reveal that neutrality does not mean lack of electrical activity. Instead, it means perfect balance over the whole particle. This internal structure also explains why the neutron behaves differently from a proton, even though they have nearly the same mass. The difference lies not in how many quarks they contain, but in how those quarks are arranged. A proton contains two up quarks and one down quark, giving it a net positive charge. A neutron swaps one up quark for a down quark, and that single change transforms its electrical identity completely. This shows how sensitive nature is to internal structure. One small change at the deepest level leads to dramatic differences in behavior. The neutron's neutrality also affects how it interacts with other particles. Because it has no net charge, it does not experience electromagnetic attraction or repulsion in the same way charged particles do. This allows neutrons to approach nuclei closely without being deflected. However, the charged quarks inside the neutron still interact indirectly through electromagnetic effects, contributing to subtle forces and moments that scientists continue to study. These hidden interactions make the neutron a rich subject for ongoing research. Another remarkable aspect of the neutron's internal structure is its magnetic behavior. Even though the neutron has no electric charge, it does have a magnetic moment. This might seem contradictory, but it arises naturally from the motion of charged quarks inside it. As the quarks move and spin, they generate tiny magnetic fields. The combined effect produces a measurable magnetic moment, even though the total electric charge remains zero. This property once puzzled scientists, but today it stands as strong evidence for the neutron's complex internal dynamics. The stability of the neutron structure is another key point. Inside an atomic nucleus, neutrons are stable for incredibly long times. However, a free neutron outside a nucleus is unstable and eventually decays into a proton, an electron, and an antineutrino. This decay reveals something profound: the neutron's internal balance is delicate. When isolated, the energy configuration inside the neutron favors transformation. Yet inside the nucleus, interactions with other nucleons stabilize it. This behavior highlights how internal structure and environment are deeply connected in the quantum world. The fact that a neutron can transform into a proton also emphasizes how closely related these particles are. At the quark level, this transformation involves a down quark changing into an up quark through the weak nuclear force. This single change alters the charge balance, turning a neutral particle into a positively charged one. Such processes show that charge itself is not rigidly fixed, but can emerge or disappear through deeper interactions, always respecting fundamental conservation laws. Understanding the neutron's internal structure has far-reaching implications. It explains why matter is stable, why elements exist, and why the universe has the structure we observe. It also connects the smallest scales of quarks to the largest scales of cosmic evolution. The precise balance of charges inside neutrons influenced how matter formed after the Big Bang and continues to influence nuclear processes inside stars. At a deeper philosophical level, the neutron teaches us that neutrality can be the result of perfect balance rather than absence. Inside the neutron, forces rage, quarks move at relativistic speeds, and energies are immense. Yet all of this complexity resolves into calm neutrality when viewed from the outside. This reflects a broader principle in nature. Harmony often emerges from opposing influences that cancel in just the right way. By looking inside the neutron, we see that its lack of charge is not a simple trait, but the outcome of an intricate internal design. The neutron is a masterpiece of balance, where positive and negative components coexist without dominance. This balance allows the neutron to fulfill its critical role in the nucleus and the universe at large. What appears silent on the surface is, in truth, a symphony of forces working together to produce one of nature's most essential particles. As scientists continue to probe deeper into the neutron's internal structure, they realized that understanding quarks alone was not enough. The way these quarks behave, interact, and fluctuate inside the neutron adds another layer of meaning to why neutrality is maintained so precisely. The neutron is not a rigid object with fixed parts, it is a dynamic system where quarks and gluons are in constant motion, exchanging energy and momentum at incredible speeds. This restless internal activity somehow averages out to perfect electrical neutrality, a fact that highlights the extraordinary precision of natural laws. One of the most striking discoveries about the neutron is that its quarks are never still. They move relativistically, meaning at speeds close to that of light, confined within an extremely small region of space. Gluons, the carriers of the strong force, are constantly being exchanged, created, and absorbed. In this turbulent environment, additional quark-antiquark pairs can briefly appear and disappear due to quantum fluctuations. These virtual particles momentarily disturb the internal charge distribution, yet the overall balance is never broken. No matter how complex the internal motion becomes, the total charge remains exactly zero. This behavior illustrates an important principle of quantum physics. Observable properties are often the result of averages rather than static arrangements. At any instant, the neutron may exhibit regions that are slightly more positive or slightly more negative, but when measured as a whole, these variations cancel out. The neutron's neutrality is therefore a global property emerging from countless microscopic interactions. This challenges the classical idea that neutrality means uniformity. Instead, it shows that neutrality can arise from constant change and internal tension. The strong force that binds quarks inside the neutron is unique among fundamental forces. Unlike electromagnetism, which weakens with distance, the strong force becomes stronger as quarks move apart. This ensures that quarks remain confined. This confinement plays a direct role in maintaining the neutron's structure. If quarks could separate freely, the delicate charge balance inside the neutron could be disrupted. The strength of the strong force guarantees that the quarks remain locked together in the precise combination that produces neutrality. The neutron's internal structure also explains why it interacts differently with external fields compared to charged particles. An electric field can easily accelerate an electron or deflect a proton, but it passes through a neutron almost unnoticed. However, because the neutron has a magnetic moment, it still responds to magnetic fields in subtle ways. This dual behavior, electrically neutral yet magnetically active, is a direct consequence of its internal composition. It allows scientists to manipulate and study neutrons using magnetic techniques while benefiting from their electrical neutrality. These properties have made neutrons invaluable tools in experimental science. Neutron scattering experiments, for example, rely on the neutron's ability to penetrate deeply into materials without being repelled by electric charges. By observing how neutrons scatter off atomic nuclei, scientists can learn about the structure of solids, liquids, and even biological molecules. None of this would be possible if the neutron carried an electric charge. Its internal balance enables it to act as a messenger from otherwise inaccessible regions of matter. The neutron structure also sheds light on why nature allows particles to transform into one another. As mentioned earlier, a free neutron can decay into a proton. This transformation involves a change in the type of quark inside the neutron. One down quark becomes an up quark, altering the charge balance. This process is governed by the weak nuclear force, another fundamental interaction. The fact that such a small internal change can flip the electrical identity of a particle shows how charge is deeply rooted in internal structure rather than being an external label. This decay process also emphasizes that the neutron's neutrality is not the lowest energy state for an isolated system. Outside the nucleus, the neutron's internal configuration is slightly unstable, leading to decay over time. Inside the nucleus, however, the presence of other nucleons changes the energy landscape. Interactions between protons and neutrons stabilize the neutron, preventing decay. This demonstrates that internal structure and external environment are inseparable in determining particle behavior. On a larger scale, the internal structure of neutrons influences the stability of entire nuclei. The way neutrons and protons arrange themselves depends on subtle quantum rules related to spin, energy levels, and interactions. Neutrons help fill nuclear energy shells in a way similar to how electrons fill atomic orbitals. Their neutrality allows them to occupy states that would be inaccessible or unstable for charged particles. This shell structure is one reason certain numbers of neutrons lead to especially stable nuclei. The role of neutrons becomes even more dramatic in extreme conditions. In the cores of massive stars, pressures and temperatures are so high that electrons and protons can merge to form neutrons. The resulting matter is dominated by neutrons packed incredibly close together. In neutron stars, the internal structure of neutrons and their interactions determine the size, mass, and behavior of these cosmic objects. Here, the same principles that govern quarks inside a single neutron scale up to govern entire stars. The precision of neutron neutrality has also become a testing ground for new physics. Scientists continually perform experiments to see if the neutron might possess an extremely tiny electric charge, far smaller than current detection limits. So far, all measurements confirm neutrality to astonishing accuracy. Any deviation would signal new physical laws beyond our current understanding. The neutron thus stands as a benchmark for testing the completeness of modern theories. From a broader perspective, the neutron's internal structure teaches us that simplicity at the surface often hides complexity beneath. The label, neutral, suggests absence, but the reality is a vibrant internal world governed by powerful forces and precise symmetries. The neutron is neutral not because nothing is happening inside it, but because everything inside it is balanced with extraordinary exactness. This balance has profound consequences. It allows the neutron to serve as a stabilizing agent in nuclei, a catalyst in nuclear reactions, a probe in scientific research, and a key player in cosmic evolution. None of these roles would be possible without its unique internal structure. The neutron's neutrality is not an accident or a coincidence. It is the natural outcome of how quarks, forces, and symmetries come together at the deepest level of matter. In the end, the neutron shows us that the universe is built not only on forces that push and pull, but also on structures that cancel and balance. Its hidden internal complexity gives rise to an outward simplicity that makes the atomic world stable and the universe habitable. By understanding what lies inside the neutron, we gain insight into one of nature's most elegant solutions, creating stability through perfect balance rather than overwhelming force. At the heart of every atom lies a region of extraordinary tension and balance. The atomic nucleus is an incredibly small space, yet it contains almost all the mass of the atom and hosts some of the most powerful forces in the universe. Protons, each carrying a positive electric charge, are packed together at distances so small that their mutual repulsion should, by all classical reasoning, tear the nucleus apart instantly. The very existence of stable atoms therefore poses a deep question: what prevents this explosion? The answer is found in the stabilizing role of neutrons, particles that quietly hold the nucleus together without adding to its electrical conflict. To appreciate how neutrons stabilize the atomic nucleus, it is essential to understand the problem they solve. Protons repel one another due to the electromagnetic force, which is long-range and extremely strong at short distances. As more protons are added to a nucleus, this repulsive force grows rapidly. In light elements, where only a few protons are present, the repulsion is manageable, but as atomic numbers increase, the repulsion becomes enormous. Without a counteracting mechanism, heavy atoms would be impossible. Neutrons provide exactly what is needed: mass and attraction without electric repulsion. Neutrons contribute to nuclear stability primarily through their participation in the strong nuclear force. This force is fundamentally different from electromagnetism. It acts only over extremely short distances, comparable to the size of the nucleus, but within that range it is far stronger than any repulsive force between protons. The strong force binds nucleons, protons and neutrons together, creating a tightly bound nuclear core. Neutrons are essential to this process because they feel and transmit the strong force without increasing electromagnetic repulsion. One of the most important features of the strong nuclear force is that it does not distinguish significantly between protons and neutrons. It binds proton-proton, neutron-neutron, and proton-neutron pairs with nearly equal strength. However, in practice, proton-neutron interactions are especially effective at stabilizing the nucleus. Neutrons act as buffers between protons, allowing the strong force to operate while keeping charged particles slightly separated. This reduces the overall repulsive stress within the nucleus and increases stability. The stabilizing role of neutrons becomes more evident as nuclei grow larger. For very light elements, such as hydrogen and helium, the number of neutrons is equal to, or nearly equal to the number of protons. This balance provides sufficient stability. As elements become heavier, more neutrons are required than protons. This increasing neutron-to-proton ratio reflects the growing need to counteract proton repulsion. Neutrons essentially dilute the positive charge density, spreading the strong force's binding effect across a larger number of particles without increasing electrical instability. This delicate balance explains why not all combinations of protons and neutrons are stable. There exists a narrow range of neutron numbers for each element that results in a stable nucleus. Too few neutrons, and the nucleus cannot hold together against proton repulsion. Too many neutrons, and new forms of instability appear, often leading to radioactive decay. The neutron's role is therefore not simply to add stability, but to fine-tune it. Nuclear stability is not a yes or no condition, it is a carefully maintained equilibrium. Neutrons also contribute to stability through quantum effects. Protons and neutrons are not just particles in the classical sense, they are quantum objects that occupy discrete energy levels within the nucleus. These levels form shells, similar in concept to the electron shells in atoms. Certain numbers of neutrons and protons fill these shells completely, leading to especially stable nuclei. These so-called magic numbers are a direct consequence of how neutrons behave inside the nucleus. Their neutrality allows them to occupy energy states without being affected by electric forces that influence protons. Another key aspect of neutron stabilization lies in the distribution of energy within the nucleus. Neutrons help lower the overall energy of the system by participating in strong force interactions that release binding energy. The greater the binding energy per nucleon, the more stable the nucleus. Neutrons increase this binding energy up to a point, making the nucleus more tightly held together. This is why medium-weight elements, with an optimal balance of protons and neutrons, are the most stable of all. The stabilizing influence of neutrons is also evident in radioactive processes. Many forms of radioactive decay occur because a nucleus has an imbalance in its neutron-to-proton ratio. Beta decay, for example, occurs when a neutron transforms into a proton, or vice versa, to restore balance. This process highlights the neutron's role as a regulator. By allowing such transformations, nature seeks the most stable configuration possible. The neutron is central to this self-correcting mechanism. In nuclear reactions, neutrons often act as the key agents of change. Because they carry no charge, they can penetrate nuclei easily, triggering reactions that would be impossible for charged particles. In nuclear fission, free neutrons strike heavy nuclei, destabilizing them and causing them to split. In fusion processes inside stars, neutrons help form heavier nuclei and redistribute energy. In both cases, neutrons influence stability by enabling transitions from one nuclear state to another. The stabilizing role of neutrons extends beyond individual nuclei to the structure of matter in the universe. The variety of elements found in nature depends on which nuclei are stable enough to exist for long periods. Neutrons determine this stability landscape. Without them, the periodic table would collapse to a handful of light elements. The richness of chemistry, biology, and material science is therefore rooted in the neutron's ability to stabilize nuclei across a wide range of sizes. From a broader perspective, the neutron's role in nuclear stability reveals a fundamental principle of nature. Stability often arises not from dominance, but from balance. Protons provide identity, defining the element through their number. Neutrons provide support, ensuring that identity can persist without destruction. They are the silent partners that make complexity possible. Even in extreme environments, the stabilizing influence of neutrons remains evident. In neutron-rich nuclei found in certain astrophysical processes, neutrons enable the creation of very heavy elements through rapid capture mechanisms. In neutron stars, matter exists in a state where neutrons dominate entirely, forming a stable structure under immense gravitational pressure. These cosmic examples demonstrate that neutron-based stability is not limited to ordinary matter, but extends to the most extreme forms of existence. Ultimately, the stability of the atomic nucleus is a triumph of cooperation between forces and particles. The neutron plays a central role in this cooperation. By carrying no charge, by engaging fully in the strong nuclear force, and by balancing the disruptive tendencies of protons, neutrons make stable matter possible. They transform what would otherwise be a chaotic cluster of repelling charges into a coherent, enduring structure. Without neutrons, the nucleus would not merely be unstable. It would not exist at all. When we continue to examine how neutrons stabilize the atomic nucleus, it becomes clear that their role is not static but dynamic. Neutrons are constantly interacting with protons and with each other through the strong nuclear force, creating a living, fluctuating system rather than a rigid structure. The nucleus is more like a vibrating drop of quantum matter than a solid object, and neutrons are essential to keeping this motion from becoming destructive. Their presence allows flexibility without collapse, movement without disintegration. One of the most important stabilizing contributions of neutrons lies in how they distribute force within the nucleus. Protons repel each other in all directions, creating internal stress. Neutrons help absorb and redistribute this stress by sharing strong force bonds across multiple neighboring particles. Instead of protons pushing directly against one another, neutrons act as intermediaries, spreading attractive forces more evenly throughout the nucleus. This reduces localized instability and allows larger nuclei to exist. As nuclei grow heavier, geometry becomes increasingly important. Protons crowd together, and the spatial arrangement of nucleons starts to matter just as much as their number. Neutrons help shape the internal structure of the nucleus by occupying positions that maximize strong force attraction while minimizing repulsion. In many stable nuclei, neutrons outnumber protons, forming a kind of neutral framework within which protons can reside more safely. This internal architecture is a key reason heavy elements do not instantly fall apart. Neutrons also stabilize nuclei through a subtle quantum rule known as the exclusion principle. Protons and neutrons are fermions, meaning no two identical ones can occupy the same quantum state at the same time. Because neutrons are distinct from protons, they can fill nuclear energy levels independently. This greatly increases the number of available stable configurations. If only protons existed in the nucleus, these quantum restrictions would severely limit stability. Neutrons effectively expand the nuclear seeding capacity, allowing matter to build upward into heavier elements. This quantum organization leads to the phenomenon of nuclear shells. Just as electrons occupy shells around the nucleus, protons and neutrons occupy shells within it. Neutrons play a crucial role in completing these shells. When neutron shells are filled, nuclei become especially stable, even if proton shells are not. Many of the most stable isotopes in nature owe their longevity to closed neutron shells. This shows that neutrons contribute stability not only through force balance, but also through quantum structure. The stabilizing effect of neutrons is further revealed when we study radioactive decay. Many unstable nuclei decay not because they lack neutrons, but because they have too many. This may seem contradictory at first, but it highlights the precision of nuclear balance. Neutrons stabilize only within a certain range. Beyond that range, excess neutrons increase internal energy and disrupt shell structure. The nucleus then seeks stability through decay, converting neutrons into protons or releasing particles. This behavior underscores that neutrons are regulators, not simply reinforcements. In beta decay, a neutron transforms into a proton, emitting an electron and an antineutrino. This process increases the proton count and adjusts the neutron to proton ratio towards stability. In other cases, a proton may transform into a neutron. These transformations demonstrate that neutrons are central to nuclear self-correction. They allow nuclei to adapt, evolve, and move toward more stable configurations over time. Without neutrons, such regulatory mechanisms would not exist. Neutrons also play a stabilizing role in nuclear binding energy. The binding energy of a nucleus is the energy required to pull it apart into individual nucleons. Higher binding energy generally means greater stability. Neutrons contribute significantly to this binding by forming strong, force connections without adding repulsive energy. As neutrons are added to a nucleus, binding energy per nucleon increases up to an optimal point. This explains why elements like iron are among the most stable in the universe. Their neutron-proton balance is near perfect. The importance of neutron stabilization becomes even clearer when we consider what happens during nuclear reactions. In nuclear fission, a heavy nucleus becomes unstable and splits into smaller ones. This instability arises partly because the nucleus contains so many protons that neutron buffering can no longer fully counteract repulsion. In nuclear fusion, light nuclei combine to form heavier ones, but only if the resulting neutron balance supports stability. In both cases, neutrons determine whether a reaction releases energy or fails to occur. Beyond laboratories and reactors, neutron stabilization shapes the cosmos. In stars, nuclear stability governs which fusion reactions can proceed and which elements can form. During stellar lifetimes, neutrons enable the gradual buildup of heavier nuclei. In violent cosmic events such as supernovae, rapid neutron capture allows the creation of very heavy elements like gold and uranium. These processes depend entirely on the neutron's stabilizing role. Without neutrons, the universe would be chemically impoverished. In the most extreme environments, neutron stabilization takes on an entirely new meaning. In neutron stars, gravity crushes matter so intensely that protons and electrons merge into neutrons. The result is a massive object composed almost entirely of neutrons, held stable by a balance between quantum pressure and gravity. Here, neutrons are no longer just stabilizers of nuclei, they become the very substance of the star. This shows that neutron-based stability can scale from the smallest atomic nuclei to objects kilometers wide. The hidden role of neutrons in stability also extends into practical human applications. Nuclear medicine, power generation, and materials science all rely on predictable nuclear behavior. That predictability exists because neutrons stabilize nuclei in consistent ways. Engineers and scientists can calculate reaction rates, decay times, and energy outputs precisely because neutron-proton balance follows universal rules. This reliability is a direct gift of neutron stability. From a philosophical standpoint, the neutron's role in the nucleus reveals a powerful truth about nature. Stability is not achieved by eliminating opposing forces, but by balancing them. Protons push outward, neutrons hold inward, and the result is harmony rather than chaos. The neutron does not dominate, does not repel, does not announce itself electrically. Instead, it quietly ensures that matter can exist at all. When we consider the atomic nucleus as a whole, we see that protons define identity, electrons define chemistry, but neutrons define endurance. They allow atoms to survive time, pressure, and transformation. Without neutrons, there would be no long-lived elements, no complex molecules, no stars burning steadily for billions of years, and no life capable of asking questions about the universe. In the end, the stabilizing role of neutrons reminds us that the most important contributions are often invisible. Neutrons carry no charge, emit no light, and leave no obvious trace in everyday experience. Yet they are the reason the atomic nucleus does not collapse into chaos. They are the quiet architects of matter, shaping stability from within, proving that in the deepest layers of reality, balance is the ultimate source of strength. Deep within the atomic nucleus, a force operates that is unlike anything we experience in everyday life. It is short-ranged, incredibly powerful, and completely indifferent to electric charge. This is the strong nuclear force, and it is the hidden stage on which neutrons reveal their silent power. While protons announce themselves through positive charge and electrons through negative charge, neutrons express their influence almost entirely through this force. Understanding the strong nuclear force explains why neutrons, despite carrying no charge, are essential to holding matter together. The strong nuclear force acts only at distances comparable to the size of a nucleus. Beyond that tiny range, it becomes almost undetectable. Within that range, however, it overwhelms every other force in nature. It is strong enough to bind protons and neutrons together against the immense electromagnetic repulsion between protons. Neutrons participate fully in this force, forming strong bonds with both protons and other neutrons. Because they carry no electric charge, they add attraction without adding repulsion, making their contribution uniquely valuable. Unlike electromagnetism, which pushes or pulls charged particles over long distances, the strong nuclear force works only when particles are extremely close. This means that neutrons must be packed tightly inside the nucleus to exert their effect. Once there, they act as connectors, linking neighboring nucleons into a coherent whole. Each neutron helps transmit the strong force across the nucleus, reinforcing stability from within. Without neutrons, the strong force would have fewer pathways to act, and nuclei would be far more fragile. The hidden power of neutrons lies in their ability to amplify attraction without causing conflict. Protons alone cannot do this, because every additional proton increases repulsion. Neutrons avoid this problem entirely. They strengthen the binding network while remaining electrically invisible. This is why heavier nuclei require more neutrons than protons. As proton repulsion grows, neutrons compensate by increasing strong force connections without increasing electrical stress. At an even deeper level, the strong nuclear force itself is a reflection of interactions between quarks inside protons and neutrons. Neutrons are not passive participants. Their internal quark structure allows them to exchange force, carrying particles with neighboring nucleons. These exchanges create an effective attraction that holds the nucleus together. Although this process is invisible to the eye and silent to instruments measuring charge, it is the dominant force shaping nuclear structure. The short-range nature of the strong force also explains why nuclei have a finite size. Neutrons cannot stabilize matter at arbitrary distances. Their influence is powerful but limited, ensuring that nuclei remain compact rather than collapsing into denser forms. This balance between strength and range is critical. Too long-ranged, and all matter would clump together. Too short-ranged, and nuclei would fall apart. Neutrons operate perfectly within this narrow window. Neutrons also influence how nuclei respond to change. When energy is added to a nucleus, such as during a collision or decay, neutrons help absorb and redistribute that energy through the strong force. This buffering effect can prevent immediate disintegration, allowing nuclei to undergo controlled transformations rather than catastrophic collapse. In this way, neutrons contribute not only to stability but also to flexibility within nuclear systems. The power of neutrons becomes especially clear in nuclear reactions. In fission, free neutrons strike heavy nuclei and disrupt the delicate balance of forces inside them. The strong force momentarily loses its grip and the nucleus splits. In fusion, neutrons help stabilize newly formed nuclei, allowing them to exist long enough to release energy. In both cases, neutrons act as keys that unlock or secure nuclear bonds. Even in extreme cosmic environments, the strong nuclear force and neutrons work together to define reality. In the cores of massive stars and in neutron stars, neutrons dominate matter. Their interactions through the strong force determine the stiffness, density, and survival of these objects against gravitational collapse. Here, the hidden power of neutrons is scaled up from the nucleus to entire stars. In the end, the strong nuclear force reveals why neutrons are indispensable despite their lack of charge. Their power does not come from attraction or repulsion in the electromagnetic sense, but from their deep participation in the force that binds matter at its core. Neutrons do not shine, push, or pull electrically, yet they hold the nucleus together with unmatched effectiveness. Their hidden strength lies in quiet cohesion, proving that the most powerful forces in nature often operate beyond what we can directly see. When we look at atoms from the outside, all atoms of the same element appear identical. Gold is gold, carbon is carbon, and oxygen is oxygen, defined by the number of protons in their nuclei. Yet beneath this apparent sameness lies a hidden variety shaped almost entirely by neutrons. Isotopes reveal that neutrons quietly control atomic identity in ways that go far beyond simple charge. By changing the number of neutrons, while keeping the number of protons the same, nature creates multiple versions of the same element, each with its own nuclear personality. An isotope is an atom with the same number of protons as other atoms of that element, but a different number of neutrons. The proton count fixes the element's chemical behavior, while the neutron count determines nuclear stability. Some isotopes are stable and persist indefinitely, while others are unstable and decay over time. This difference comes not from charge, but from neutron balance. Neutrons decide whether an atom will endure quietly or transform through radioactive processes. The presence of different isotopes explains many mysteries in both nature and science. For example, carbon exists primarily as carbon-12, with 6 protons and 6 neutrons, which is stable and abundant. Carbon-14 with 2 extra neutrons is unstable and radioactive. This single difference gives carbon-14 a unique role in archaeology and geology, where its slow decay allows scientists to date ancient organic materials. Here, neutrons directly shape our understanding of history and time. Neutrons also influence the mass of atoms. Each additional neutron increases atomic mass without changing charge. This affects how atoms behave in physical processes such as diffusion, vibration, and bonding at a subtle level. While chemical reactions are largely insensitive to neutron number, physical properties can vary slightly between isotopes. These small differences have important consequences in fields ranging from climate science to medicine. Isotopes play a critical role in nuclear energy. In nuclear reactors, not all isotopes of an element behave the same way. Uranium-235, with fewer neutrons than uranium-238, is easily fissioned by slow neutrons, making it useful for energy production. Uranium-238 with more neutrons is more stable and does not readily undergo fission. The difference between these two isotopes determines the entire design of nuclear reactors and the feasibility of nuclear power. Neutrons also shape atomic identity through radioactive decay pathways. When an isotope is unstable, it decays in ways that change its neutron to proton ratio. This process moves the atom toward a more stable configuration, sometimes transforming it into a different element altogether. These decay chains reveal that atomic identity is not fixed forever, but can evolve over time. Neutrons act as the variable that allows this evolution to occur. In the natural world, isotopes tell stories about origin and movement. Scientists analyze isotope ratios in water, rocks, and biological tissues to trace climate patterns, migration routes, and environmental changes. These techniques rely entirely on neutron differences. The atom's invisible interior becomes a record of past events, written in neutron counts rather than electric charge. In stars, isotopes determine which nuclear reactions can occur. Stellar fusion pathways depend on whether certain isotopes are stable long enough to capture additional particles. Neutrons enable the formation of heavy isotopes in stellar interiors and during explosive events like supernovae. The elements that make up planets, oceans, and living organisms were forged through neutron-driven isotope processes in stars long before Earth existed. Neutrons also give rise to isotopic diversity that benefits life directly. In medicine, radioactive isotopes are used for imaging and cancer treatment. Their predictable decay rates, determined by neutron imbalance, allow precise control over radiation exposure. In agriculture, isotopes help study nutrient uptake in plants. In industry, isotopes are used to inspect materials and detect flaws. All of these applications depend on the neutron's role in shaping atomic identity. The existence of isotopes shows that charge alone does not define matter. Two atoms can be electrically identical yet behave very differently because of neutrons. This challenges the idea that what we see from the outside tells the whole story. Neutrons introduce depth, variation, and time into atomic existence. They allow atoms to be stable or unstable, light or heavy, ordinary or extraordinary. Ultimately, isotopes demonstrate the hidden influence of neutrons in the atomic nucleus. They reveal that atomic identity is layered, with charge defining outward behavior and neutrons defining inner fate. Through isotopes, neutrons shape energy, history, technology, and life itself. Quietly and invisibly, they ensure that matter is not uniform and static, but rich, diverse, and dynamic across the universe. Neutrons play a decisive role in nuclear reactions and energy, acting as both initiators and regulators of some of the most powerful processes in nature. Unlike charged particles, neutrons can move freely into the heart of an allotropic nucleus without being repelled by electric forces. This single property makes them uniquely capable of triggering nuclear transformations that release enormous amounts of energy. From the fire of stars to the controlled reactions inside nuclear reactors, neutrons are central to how energy is produced and transformed at the nuclear level. In nuclear fission, neutrons are the key that unlocks the energy stored inside heavy nuclei. When a slow-moving neutron enters a heavy nucleus such as uranium-235, it destabilizes the delicate balance of forces holding that nucleus together. The strong nuclear force can no longer maintain cohesion against internal repulsion, and the nucleus splits into two smaller fragments. This process releases a tremendous amount of energy, along with additional neutrons. These newly released neutrons can then trigger further fission events, creating a chain reaction. Without neutrons, this cascading release of energy would be impossible. The neutrality of neutrons is essential in this process. Charged particles would be deflected by the positively charged nucleus before reaching its interior. Neutrons, unaffected by electric repulsion, slip directly into the nucleus. This allows nuclear reactions to occur at relatively low energies compared to what would be required if charged particles were involved. The efficiency of nuclear fission depends entirely on this property. Neutrons also govern the behavior of nuclear reactors. By controlling the number and speed of neutrons, engineers can regulate the rate of fission. Materials called moderators slow down fast neutrons, increasing the likelihood that they will cause further fission. Control rods absorb neutrons, reducing reaction rates. Every aspect of reactor design revolves around neutron management. Energy production is not just about splitting atoms, but about guiding neutrons with precision. In nuclear fusion, which powers stars, neutrons play a different, but equally important role. Fusion involves light nuclei combining to form heavier ones, releasing energy in the process. In the Sun, hydrogen nuclei fuse to form helium, producing enormous amounts of energy. Neutrons appear in later fusion stages, and in more massive stars, where they help form heavier elements. They often carry energy away from fusion reactions, redistributing it throughout the star and influencing stellar evolution. Neutrons are also crucial in the creation of elements beyond iron. In stellar explosions such as supernovae, intense neutron fluxes bombard atomic nuclei. Through rapid neutron capture, nuclei absorb neutrons faster than they can decay, forming very heavy elements. Gold, platinum, and uranium owe their existence to these neutron-driven processes. Energy released during these events shapes galaxies and seeds the universe with complex matter. On Earth, neutron interactions are harnessed in many practical ways. In medicine, neutron radiation is used in certain cancer treatments because it interacts differently with biological tissue than other forms of radiation. In research, neutron beams allow scientists to study materials at the atomic level. These applications rely on the neutron's ability to penetrate matter and interact with nuclei without electric interference. Neutrons also play a role in nuclear safety and waste management. The long-term behavior of radioactive waste depends on neutron-induced reactions and decay pathways. Understanding how neutrons interact with different materials helps engineers design safer storage and containment systems. Once again, the neutron's neutrality and nuclear interactions are central to controlling energy over long timescales. The role of neutrons in energy extends even to future technologies. Experimental fusion reactors aim to replicate stellar fusion on Earth. Managing neutron production and absorption is one of the greatest challenges in these designs. Neutrons carry much of the energy produced in fusion reactions, and capturing that energy efficiently is critical for making fusion a viable power source. Throughout all these processes, Neutrons act as silent carriers of energy and change. They do not announce their presence with charge or light, yet they shape the most powerful reactions known to science. Their ability to enter nuclei, trigger transformations, and release energy makes them indispensable to both natural and human-made energy systems. In the end, the story of neutrons in nuclear reactions is a story of access and influence. By carrying no charge, neutrons bypass barriers that stop other particles. By interacting through the strong force, they unlock energy stored deep within matter. From the burning of stars to the electricity powering cities, neutrons quietly stand at the center of the nuclear energy that shapes our universe. Beyond the boundaries of the atom and the controlled environments of laboratories, neutrons play a hidden yet profound role in the universe and in modern technology. Their lack of electric charge allows them to move through matter and space in ways no charged particle can, making them key actors in cosmic events and powerful tools in human innovation. From the birth of elements in stars to advanced medical treatments on Earth, neutrons quietly influence both the grand scale of the cosmos and the practical details of everyday life. In the universe, neutrons were among the first building blocks to shape matter after the Big Bang. In the earliest minutes of cosmic history, protons and neutrons combined to form the first atomic nuclei. The ratio between these particles determined how much hydrogen and helium the universe would contain, setting the stage for the formation of stars and galaxies. The neutron's neutrality allowed it to participate freely in these early nuclear reactions, influencing the chemical composition of everything that followed. Inside stars, neutrons continue to play a decisive role. Stellar fusion relies on a delicate balance of forces, and neutrons help stabilize newly formed nuclei long enough for energy to be released. In massive stars, neutron-related processes enable the formation of heavier elements through slow and rapid capture mechanisms. When these stars explode as supernovae, enormous numbers of neutrons are released, driving the creation of elements heavier than iron. The gold in jewelry, the uranium in reactors, and the iodine in the human body all trace their origins back to neutron-rich cosmic events. One of the most extreme expressions of the neutron's cosmic role is the neutron star. When a massive star collapses under gravity, protons and electrons merge to form neutrons, creating an object composed almost entirely of neutron matter. These stars are incredibly dense, with a single teaspoon of their material weighing billions of tons. The behavior of neutrons under such extreme conditions determines the size, stability, and lifespan of these stars. Studying them allows scientists to test fundamental theories of matter and gravity. Closer to home, neutrons have become indispensable tools in science and industry. In materials science, neutron scattering techniques allow researchers to see inside materials without damaging them. Because neutrons can penetrate deeply into solids and interact with atomic nuclei, they provide detailed information about structure, motion, and magnetic properties. This has led to advances in electronics, energy storage, and manufacturing. In medicine, neutrons are used in both diagnosis and treatment. Certain cancer therapies employ neutron radiation because it can be more effective against specific tumor types. Neutron-based imaging techniques help doctors study the behavior of biological systems at a molecular level. These applications rely on the neutron's ability to interact with nuclei while bypassing the electric barriers that limit other particles. Neutrons also contribute to security and environmental monitoring. Neutron detection systems are used to identify hidden nuclear materials, helping prevent the spread of nuclear weapons. In environmental science, neutron measurements help analyze soil moisture and study climate processes. These technologies take advantage of the neutron's unique interactions with matter to reveal information that would otherwise remain hidden. The role of neutrons extends into energy research and future technologies. In advanced nuclear reactors and experimental fusion systems, neutrons carry a significant portion of the energy produced. Capturing and managing this energy efficiently is one of the key challenges in developing next generation power sources. Success in this area could provide cleaner and more sustainable energy for the world. Even in space exploration, neutrons provide valuable insights. Instruments on spacecraft measure neutron emissions from planetary surfaces to detect water and other elements. Such techniques have been used to identify water ice on the Moon and Mars, shaping plans for future exploration and potential habitation. Here again, neutron behavior reveals hidden truths about distant worlds. What makes the neutron so valuable in all these contexts is the same property that defines it at the atomic level: neutrality. By carrying no charge, neutrons avoid interference from electric fields, allowing them to travel, penetrate, and interact in unique ways. This property makes them ideal messengers, carriers of information from places that are otherwise inaccessible. In the end, the neutron's hidden role stretches from the smallest nucleus to the largest cosmic structures. It helps create elements, power stars, diagnose disease, protect societies, and explore planets. Quiet and invisible, the neutron bridges the gap between the fundamental laws of physics and the complex world we live in. Its influence reminds us that some of the most important forces shaping reality work silently, behind the scenes, holding the universe together and pushing human knowledge forward.